We appreciate you taking the time to be here. I'm Keith Brandt. I'm the Vice Chancellor for University Relations at UC Santa Cruz. And welcome to our second annual Original Thinkers event in Southern California. Let's see, before I introduce our speakers, I want to do a little poll. So how many of you out there are alumni of UC Santa Cruz? Okay. We have about 21,000 alumni in Southern California, so you're representing them tonight. Thank you. How many current students or current parents, parents of current students? Oh, almost about an equal number. Well, you're very dedicated for being here because it's spring break and you could be off doing a lot of interesting things. So thank you for being here. And finally, how many of you are newly admitted to UC Santa Cruz and you're here because you're considering becoming a banana slug? Okay, whoa. Well, a special welcome to all of you. We appreciate you coming. So when we have a group of people gathered, I always like to give you a few facts about UC Santa Cruz, so some takeaways. So first of all, UC Santa Cruz is a very diverse university, one of the most diverse in California these days. Our student body is about 30% Latino, about 25% Asian American, about 4% African American, and about half of all our students are first generation in their families to go to college. So it's very different than the Santa Cruz that evolved 50 years ago. Second thing, we're very much devoted to environmental sustainability at UC Santa Cruz. A year and a half ago, we renamed College 8 to Rachel Carson College in recognition of the environmental pioneer. We did a poll recently and found almost about a half of our faculty are engaged with some aspect of sustainability, environmental sustainability in their research. So that's very exciting in terms of sustainability. And then I want to just give you some idea of where we pair in some rankings and some academic successes. You'll hear a little more about this tonight, but our astronomy and astrophysics department is considered among the best in the world. UC Santa Cruz is a pioneer in organic farming and continues to operate an extensive research farm and garden program. Our marine science programs are outstanding. This fall, we'll have the first cohort for a new master's degree in coastal science and policy. This is our first entree into mixing science and policy in a degree program. This is dangerous to say in Southern California, I know, in LA, but we were recently chosen one of the country's best colleges for undergraduate film majors. Yeah. And our students are very committed to such things as SocDoc, which is social documentary and things that are part of our social justice mission. Our graduate and undergraduate computer game design programs are in the top 20 in the nation, and actually we're #2 in California, so it's very exciting. And again, for about the 5th year in a row, we're ranked in the top 3 in the world for research influence based on the Times Higher Education ranking. Now that's a little bit of a esoteric ranking in academia, but really what it does is it calls out the caliber of the faculty at UC Santa Cruz because it logs the number of times faculty are cited in publications by other faculty. So that's how good our faculty are. We're #3 in the world. We're up there with MIT and Stanford in that listing, which is very exciting. And on top of that, our faculty are still very devoted to teaching undergraduates, which makes us unique in the world of research institutions. So tonight you're going to get a taste of some of our faculty, a grad student, and we'll start off by hearing from an alum. Let me introduce them. I'm going to introduce all 4 of them and then get out of the way for you. So our first talk is from Porter Provost and Literature Professor Sean Keilen. Sean is also director of the Shakespeare Workshop, a program of the Humanities Institute. Together, we're going to learn what Shakespeare, Caesar, and the humanities can tell us about the interesting time we live in today. Then we're going to fast forward from the 17th century to August 17th of this past year. Graduate student Dave Coulter is going to tell us the untold story of a major scientific discovery, an exciting day for us and for scientists all over the world. And then Enrico Ramirez Ruiz, chair of our astronomy and astrophysics department, will take us on a journey from Aztec legend to the galaxies, to what we're made of, and how the discovery in August ties it all together. But to begin, we have a special guest here to say a few words, alumna Tracy Fullerton. As we celebrate at UC Santa Cruz the Year of Alumni, we take great pride in people like Tracy. Now an accomplished game designer and director of the games program at USC, Tracy studied literature and theater arts at UC Santa Cruz. This was before we created Games and Playable Media program. But from the class of 1988, please welcome Tracy Fullerton.
Hi there. I don't want to take too much of your time, but I just wanted to talk. I was asked to talk a little bit about my path from Santa Cruz to being a game designer, which is a kind of odd path, if you will. Studying theater arts and English literature doesn't seem to be a direct line to working in the world of technology and game entertainment. But for me, it had a kind of a logic that was built during my time at Santa Cruz, because we were encouraged to do so much experimentation. While I was at Santa Cruz, I was at Porter College, yay Porter. And Porter was the arts college. But also there were really interesting faculty there that were doing experimentation in digital music, for example. And I remember also taking a course in the sciences, which was computers and society. And just a strange aside, my final paper for that class, I went and interviewed people who were building some of the earliest digital editing systems in Silicon Valley, and they told me that it was a long shot, but it's possible that we might be able to digitally edit video in the future. These kinds of interconnections between theater, film, the arts in general, the humanities, and emerging digital media is really what set me on my path. And I grew a strong interest in experimental narrative, what I call nonlinear narrative, right? So where you would get to actually change the story as you move through it. And that was most logically expressed, I found, in playful media, in things that were akin to games. And so I found myself going into the game industry and making games that were, well, a little odd. I made games that brought together some of the earliest massively multiplayer casual games, game shows. For people like Sony, I did Jeopardy and Wheel of Fortune online. But these weren't really engaging my creative energies as much as I would have liked. So I started making experimental games that were dealing more with characters and stories and a kind of sense of emotion in the gameplay. And that's when I moved into academia and I began to build the program at USC. Sorry, I didn't go back to Santa Cruz and build it there. I could have, would have loved to, but at the time I was here in LA. And we began to build a program and an experimental research lab around making games that would touch the human experience, not just in the sense of competition and a kind of direct, violent aggression, but also express all of the other aspects of creativity that had so interested me when I was an undergraduate at Santa Cruz. So just as an example, and again, I don't want to take up too much of your time, my latest game ties together my love of nature and my love of literature and my love of play, and it's a game where you play as Henry David Thoreau at Walden Pond. It's a large, immersive, first-person world, a simulation, a deep simulation of that space based on geographical data, but also Thoreau's own surveys, blooming data of plants and animals, and it changes over the course of the in-game year as you play out Thoreau's experiment in living simply. And you engage with many of the themes and the the historical moments that were surrounding that experiment. So to me, it all is a bookend to what I'm doing now, trying to push the medium of games, and what I learned at Santa Cruz. And I just would say thank you to the community, which you are all a part of.
It's the first uplifting experience I've had in a long time. Okay, so research in the humanities, like research in the natural sciences, which you'll hear about later tonight, is a search for the truth and an effort to increase our knowledge about the world. When I talk about the world, however, I don't mean the physical universe. I mean the global habitat of human cultures, the beliefs and institutions and traditions that billions of people, living and dead, create all the time from the languages that they use, that we use, to read and think and speak and listen and write. So to study the humanities is to make a commitment to that world and a commitment to liberating human beings from the tyranny of false ideas that we have about each other and ourselves. And those ideas are also part of the world that we create together in language. The humanities remember what we forget, and they call attention to life experiences that we overlook or would prefer to ignore. The humanities keep us honest. If the humanities often seem intent on making simple things very complicated, if they question sacred truths in ways that make us feel very uncomfortable, and if they can't leave well enough alone, and if you've met any of my colleagues, you know what I'm talking about, that's because the humanities are devoted to the idea that although our ancestors first developed the capacity to tell stories approximately 70,000 years ago, human experience is still a vast, vast continent that we have scarcely begun to explore. Research in the humanities expresses the belief that every life has value and meaning, and that every life story is worth understanding in its context. In the words of the Roman playwright Terence, which the humanities take as their motto, "Nothing human is alien to us." So now for the most original thinker of them all. Whoops. There he is. I'm the director of Shakespeare Workshop, which is a research center in the Humanities Institute at UC Santa Cruz. And in Shakespeare Workshop, we're aspiring to learn more about Shakespeare's writing and the global impact that it's had since the late 16th century. Shakespeare has been translated into more than 100 languages and performed millions of times on every continent apart from Antarctica, and who knows what they're really doing down there. For the last 36 years, a professional theater company has been performing Shakespeare's works in Santa Cruz during the summer. Thanks to Santa Cruz Shakespeare, as that company is now known, and to the faculty and students who support its mission, Shakespeare's works have come to be a lingua franca in which the university and the community can explore topics of shared concern. So since the workshop was established in 2013, we have investigated a translation of Shakespeare's sonnets into sign language by a deaf poet and actor called Monique Holt. And we've investigated what inmates at San Quentin and other jails are doing with Shakespeare to understand the choices that led to their convictions and to live better lives in prison. This is San Quentin's production of Julius Caesar. We've looked into the use that military veterans are making of Shakespeare to cope with post-traumatic stress disorder and to reconcile their experiences at war with the experience of living at home with civilians. This is Stefan Wolfert, who's an absolutely amazing veteran and actor who's created a program called Decruit, which uses Shakespeare and other dramatists to help veterans return from conflict. And finally, we've also done a program about the way that Shakespeare's plays might help us to understand the phenomenon of anger in relation to the 2016 presidential election. That's the poster for that event. So I'm drawing your attention to these programs in order to make the point that even if you study an author who died nearly 500 years ago, the humanities will bring the times in which you live into very fresh perspective. For me, their value has always been that they change how I understand my life by increasing my capacity to listen to other people and to imagine how they think and feel. When I talk to you about the truth that we're seeking in Shakespeare Workshop in this way, I'm thinking about something that James Baldwin wrote in 1964 in an essay that he called Why I Stopped Hating Shakespeare. And there's James Baldwin at the foot of the Albert Memorial in London, standing next to Shakespeare, as it happens. Baldwin grew up believing that Shakespeare, who was the preeminent example of English and of white European culture for him, was one of the authors and architects of my oppression. But that changed for him when he went to see the tragedy of Julius Caesar. After he saw that play, Baldwin said that he saw himself and the languages that he spoke, especially English, and his experience living as a black man in the United States very differently. And here's a passage from near the end of the essay that I'd like to share with you. My relationship to the language of Shakespeare revealed itself as nothing less than my relationship to myself and to my past. Under this light, this revelation, both myself and my past began slowly to open, perhaps the way a flower opens at morning, but more probably the way an atrophied muscle begins to function or frozen fingers to thaw. That's the kind of discovery that we're aiming at in Shakespeare Workshop. All of the research that we do in the hope of revealing something about ourselves that will restore motion to the parts of our hearts and minds in which paralysis has taken hold. So, inspired by Baldwin and by recent events, I've been teaching Julius Caesar this quarter. Like all of Shakespeare's Roman plays, this one is a tragedy, and it's focused on a period of violent transition between different kinds of government. The play is an invitation to think about the circumstances that led to the downfall of the Roman Republic and to the rise of the Roman Empire. And Shakespeare is focused on the period between 44 and 42 BC. In reality, Rome's transition between Republic and Empire unfolded in a different time frame. Between 49 BC, when Caesar crossed the Rubicon River and led an army into the Roman homeland, which was a blatant violation of law and a capital offense, and 27 BC, when the Roman Senate transferred all of its authority and power to Caesar's heir, Octavian, by awarding him the title princeps, from which we get the English word prince. When Shakespeare imagines how the Roman Republic fell, he draws our attention to a few key events: the appointment of Julius Caesar as a magistrate in perpetuity, Caesar's assassination shortly after that by Marcus Junius Brutus and other Roman senators, and the outbreak of a civil war between elites who supported the assassins and elites who supported Caesar. But let me be absolutely clear that Shakespeare is not a historian, and the play is not a documentary or a work of scholarship. He's very selective about the facts that he draws from ancient sources, and the ambiguity that results from his approach to his reading is one of the great glories of this play. Every theater company and every audience must grapple with the fact that Shakespeare does not determine for us whether Caesar or Brutus is to blame for the fall of the Roman Republic, which extinguished elected government in Western Europe for nearly 1,000 years. Did the tyrant or the patriot kill the Republic? Or maybe I should say, the popular leader or the resistance? These are the kinds of questions that the play poses very uncomfortably but resolutely refuses to answer. And it's one of the reasons why I enjoy working on it. So Julius Caesar has something of a unique relationship to American history and politics. The play comes to the fore in the American theater whenever we're most doubtful about our identity as a nation and our ability to live together peacefully. Productions of Julius Caesar are often symptoms of some kind of crisis and even a perception that we are a grave danger to each other. And I'd like to give you a few examples of that tendency in American theater. So in November 1864, as the Civil War stretched into its 4th year, John Wilkes Booth, whom you see there on the left, an actor who vigorously opposed the end of slavery, appeared with his brothers in a performance of Julius Caesar in New York City. Booth played Caesar's friend and his ally, Mark Antony, and the production raised money for the statue of Shakespeare that stands in Central Park. When Booth shot Abraham Lincoln the following April in a theater in Washington, he made it clear that fate had cast him in the role of another Roman from Shakespeare's play, not Mark Antony, but Marcus Junius Brutus, the politician who led the plot to assassinate Caesar. In a letter that Booth hoped would be published in the national press, he quoted Shakespeare's play as evidence that the killing was an act of patriotism, meant to reestablish in a divided nation what he called every tie which we once revered as sacred. In November 1937, Orson Welles' production of Julius Caesar at the Mercury Theater in New York City drew attention to the dangers posed to free republics by the rise of Nazism in Germany and of fascism in Italy. Welles appears to have played Brutus as an intellectual who has forebodings about Caesar's popularity and rise to power. Audiences and critics praised this production for showing Americans what it might feel like to live in an authoritarian society. And the production also seems to have underscored that democratic institutions, processes, and values, such as the right to assemble and seek redress of grievances, are easily co-opted for anti-democratic purposes. In 1969, at the height of the Vietnam War, a group of students at UC Santa Cruz, working under the direction of Sheldon Feldner and using costume designs by Jack Kirby, an illustrator for Marvel Comics, performed a version of Julius Caesar that they called SPQR. That's the Roman Republic's equivalent of USA. It means the Senate and the people of Rome. According to the playbill, which you see there, this production drew attention to the corrosive effects of political rhetoric and public posturing and the reporting of the news in an era of slogans, demonstrations, reprisals, and demagoguery. Television, in particular, was subject to a withering critique. I'm delighted to tell you that next year, which will be the 50th anniversary of SPQR, Shakespeare Workshop and the Humanities Institute and Porter College and Santa Cruz Shakespeare will all be working together with alumni and a new group of students to study, celebrate, and revive this production. Whoa, what just happened there? Did I do that? Okay, there it is. Jack Kirby, by the way, to recover from that, Jack Kirby, by the way, called this illustration Beloved Unwashed. What you see there are UCSC students dressed as Roman citizens. I fervently hope that the university will take Beloved Unwashed as the slogan for the next capital campaign. Okay, so, and a final note from American theater history. I didn't want to do that again. Yeah. Last June, following the 2016 elections, Oscar Eustis in the Public Theater performed Julius Caesar in Central Park. Here you see a scene from that production. Despite the director's argument that neither Shakespeare nor the Public Theater could possibly advocate violence as a solution to political problems, and certainly not assassination, the resemblance between the actor playing Julius Caesar and Donald Trump led to well-publicized protests from the right end of the political spectrum. No protests were heard from either right or left in 2012, when an African-American man who resembled Barack Obama was cast as Caesar at the Guthrie Theater in Minneapolis. So these most recent productions of Julius Caesar, and many more that are now in the pipeline in England and the United States, have a tendency to present Shakespeare to us as a moralist, and to present his plays as lessons about politics that we really must learn. I don't deny that Shakespeare is drawn to ethical questions in his plays, but I don't believe that he intended his plays to teach us any lessons. Julius Caesar is so much more than a warning about the consequences of using non-democratic methods to preserve democracies, or an opportunity to make comparisons between Julius Caesar and Donald Trump, which are, quite frankly, an insult to Caesar. Yeah, take that in for a moment. So specifically, I believe that Shakespeare's play is a resource for thinking about the impediments to communicating with each other in a society that guarantees freedom of expression, where technically there should be none. Characters in the play refer to their society as a commonwealth. They invoke a shared history. They call each other brother. But these ways of speaking about themselves and their society do not really reflect the circumstances of their life in a republic. Shakespeare lived and died as the subject of a hereditary monarch, but he understood what makes a republic fundamentally different from a monarchy. He understood that whereas in a monarchy, one person has a monopoly on political authority, in republics, political authority is shared by many people. For Shakespeare, it follows from that thought that a republic is bound to be a society that is divided against itself. He suggests that a republic is not a union of values and perspectives, but an equilibrium of opposing forces, each with an idea of what the society is and should be that is incompatible with the others. This is an illustration from Coriolanus, which is Shakespeare's final Roman play, but I think it captures the essence of republican life as Shakespeare gives it to us in Julius Caesar. In that text, Rome's commonwealth beats with what one character calls the heart of controversy. In a divided society, such as all republics must be from Shakespeare's point of view, there is a risk that politicians will come to regard their political opponents as enemies of the state. And when politicians apply themselves to defeating one another rather than to governing together, the distinction between politics and warfare becomes obscure. When Caesar's adversaries murder him during deliberations in the Senate, the difference between word and sword disappears entirely, and perhaps it was nothing more than a trick of spelling to begin with. Or to put it another way, a society that is divided against itself, a society where the distinction between politics and warfare is uncertain, must be a dangerous society. Shakespeare uses the word danger or dangerous 15 times in Julius Caesar, which is more than any other play that he wrote. He seems especially interested in what living with a sense of danger does to our capacity for self-reflection and for acknowledging perspectives that differ from our own and for being changed by them. The tragedy of Julius Caesar suggests that in a dangerous society, ordinary citizens and politicians are apt to become rigid in their perceptions of reality. Presumably, a republic's institutions exist so that people of different points of view can achieve consensus through mutual persuasion. But among politicians in Shakespeare's Rome, it is a point of honor and a proof of virtue not to change, not to compromise, not to yield to anybody. Here is Caesar, praising his own steadfastness to the men who are about to kill him. I could be well moved if I were as you, but I am constant as the northern star, of whose true fixed and resting quality there is no fellow in the firmament. The resistance to persuasion that many characters in the play exhibit has a lot to do with the way that the Renaissance imagined rhetoric and eloquence. This image shows you how eloquence looked in the mind's eye of Shakespeare's era. On the left, that's Hercules, as treatises about rhetoric often represented him. Despite his bow and his club and the lion's skin that barely covers him, Hercules does not symbolize brute force. On the contrary, in the words of one writer, he represents a man of great wisdom, whose speech links all men together by the ears in a chain to draw them and lead them even as he wishes. For Shakespeare's period, eloquence was the persuasive discourse of a good person. It was a civilizing power that could draw people out of isolation and barbarism into communities where the framework of law and custom would give order to their relationships. And because it works against a human propensity towards self-interest, persuasive discourse is inherently coercive. According to this theory, to be captivated by wise speech is really to be held captive, to be made prisoner, and to be forced to change, and to change in the direction of peaceful and productive relationships with other people. And that's how it's supposed to work anyway. About the possibility that wicked men might be persuasive, ancient and Renaissance theories of rhetoric are mostly silent, although one does find acknowledgement that persuasive speeches uninformed by good character are sometimes called weapons in the hands of madmen. So these assumptions may help us to explain why characters in Shakespeare's play believe that it's an achievement to move other people with language, but evidence of failure to be moved themselves. The Latin root for the English word danger is dominium, which means the power of a lord or master, the power to dispose of, or to hurt, or to harm. Shakespeare seems to understand that to look through somebody else's eyes, or to listen with someone else's ears, which is the very essence of being open to persuasion, means putting oneself in someone else's power. And he understands that in a dangerous society, the barriers to taking that risk are high, despite the fact that the freedom to share political authority with other people depends on our ability to imagine each other's circumstances correctly and to yield to one another. In this play, an inability or an unwillingness to look through the eyes of other people or to listen with their ears makes one a much worse interpreter of the world. Shakespeare reasons that in a dangerous society, everyone will have a tendency to interpret ambiguous information in ways that confirm their deepest convictions and their worst fears about other people. Prior to the murder of Julius Caesar, for example, a significant part of the play is given to conversations about strange weather and unusual events in the nighttime sky, and to rumors and bad dreams and omens and anonymous messages posted in public places. This is the fake news and the Twitter feed of Shakespeare's ancient world. In every case, these conversations result in a rejection of slow thinking and critical reflection, or in a hardening of perspective. And they also result in a belief that the only appropriate response to uncertainty is immediate, violent action. Here is Casca, one of the conspirators against Caesar, ruling out that there could be any explanation for what he has seen apart from his own unexamined beliefs. When these prodigies do so conjointly meet, let not men say, "These are their reasons, they are natural, for I believe they are portentous things unto the climate that they point upon." Now, Casca believes that he's making good judgments about the information that is available to him, but the play suggests otherwise. The play suggests that by refusing to consider other explanations for reality, citizens like Casca are renouncing their freedom to think critically about themselves and other people. In the process, they also deliver themselves into the hands of ambitious politicians who do not want them to think at all, but only to feel angry and afraid. A dangerous society, from Shakespeare's point of view, tends to change thinking citizens into inert metal that can be wrought by politicians. For example, in this scene. When Mark Antony persuades Rome's citizens to weep for Caesar's death, they pour forth a sudden flood of mutiny. They take the law into their own hands. They set fire to Rome. Then the play shifts from Rome to the battlefield of a civil war. Senators turn into soldiers. The citizens of Rome disappear from the play, along with the republic that guaranteed their political freedom, and they never return. I think these harrowing events, during which fast rhetoric trumps slow thinking, gave me and gave my students occasion to ponder two disturbing ideas in relation to our divided states of America. First idea: the freedom to express oneself and to appeal to other people for sympathy in politics is one of the greatest benefits of living in a republic, of living in this republic. But in a dangerous society, ambitious politicians will use that freedom as a tool to destroy the form of communal life in which everybody shares authority. That's Marlon Brando as Mark Antony. Mark Antony says, as he watches Rome burn after this speech, "Fortune is merry, and in this mood will give us anything." By us, he means himself alone, not the citizens whom he earlier addressed as friends and countrymen. Second disturbing idea: the belief that in order to be virtuous, one must turn a deaf ear to different voices paradoxically increases the likelihood that one will be enthralled by false information and bad arguments and manipulative appeals to fear and anger. That's Mark Antony after his speech as the citizens begin to destroy Rome. In Shakespeare's play, these Romans are so ready to believe whatever they are told, provided that it confirms their biases, that you might conclude that they would rather be ruled than be free. So it's only natural that in times of uncertainty and danger, people turn to Shakespeare and other great writers for guidance. But as I have been trying to suggest, Shakespeare offers mysteries to ponder rather than advice to implement. The value of reading Shakespeare and of studying the humanities is not the solutions that they provide to our problems, in my opinion. It's the questions that they pose about our circumstances. This quarter, my students and I found ourselves asking a new question. In a society that's saturated with passionate arguments and false information, how should we listen to what other people have to say? When Baldwin describes the effect of Julius Caesar on his own life, he credits the play with revealing the costs of holding fast to what he calls a desperate single-mindedness. He says that single-mindedness operates to distort and diminish a man, to distort and diminish us all. He implies that single-mindedness is what withers muscles and paralyzes them. Single-mindedness is the cold that freezes fingers in the passage from the essay that I showed you earlier. Baldwin also says that Shakespeare's play makes some of the self-protective veils between oneself and reality fall away. He says it reveals that one is not and never will be innocent for the reason that nobody is. When I put those two statements together, I understand Baldwin to be saying that although our experiences and choices shape who we are, we don't have to be limited by them or by the history that precedes us all. And if you pause for a moment to think about it, that is an extraordinary thing for Baldwin to be saying in 1964. As a gay black man in the midst of the struggle for civil rights in this country, Baldwin is suggesting, on the basis of his encounter with Shakespeare, that it's possible for us to admit who we are and to acknowledge each other and our collective past without illusions, but also without recrimination or shame. What would it be like to see our circumstances through those eyes? Well, it would be like being Baldwin, and it would be like being Shakespeare, whom the Romantic poets admired for being myriad-minded, not single-minded. They believed that Shakespeare saw the whole of human experience without embarrassment and refrained from passing judgment on it. In the tragedy of Julius Caesar, the character who most exhibits that myriad-mindedness that the Romantics admired in Shakespeare is Cicero. Cicero is the Roman statesman and orator who appears to have invented the humanities in the sense that he is the first person to use the word humanitas to describe the highest goal of an education that aspired to lead students to careers in public service and to lives of private flourishing. This seminal figure of the humanities passes very quickly over Shakespeare's stage. He doesn't have many lines, but he does pause to respond to Casca's declaration of single-mindedness, which I showed you earlier. This is what he says. "Indeed, it is a strange disposed time, but men may construe things after their fashion, clear from the purpose of the things themselves. The awareness that one's deeply held convictions might be wrong, the courage to acknowledge that other people have reasons to think, feel, and act differently from us, the capacity to postpone judgment in a strange disposed time, the capacity to hope that things can turn out better in this republic than they did in Rome. These are a few of the reasons why I study Shakespeare, and why I also believe that the humanities are the best resources that we have for living together in our dangerous republic, where liberty depends on our capacity to listen to each other and to be in each other's power without becoming angry or afraid." Thank you very much. And now I'd like to call Dave Coulter to the stage.
So I'd like to tell you a story of how we obtained the first ever visible light picture of a gravitational wave source. And that story begins at a prospective dinner for newly admitted graduate students to the astronomy department. So I was admitted, and I was interacting with the other students and the faculty, and I see Ryan Foley. I didn't know that at the time, across the room, and I introduced myself, and I say, "Hello, what university are you visiting from, and are you planning on attending UC Santa Cruz?" And he puts his hands up and he says, "You have it wrong, I'm actually a professor." To which I chuckle and I say, "Yeah, me too." So I tell that anecdote because for me it's emblematic of our relationship ever since then. And I think that there's something that informs that. It's my path to how I got here. I myself was a student of the humanities. 15 years ago, I got a degree in history, took a left turn, learned how to program computers, and then worked in the software development industry for about a decade. In that time, I wanted something more, so I went to night school, got a degree in physics that eventually prepared me for a course of study at UC Santa Cruz. So when I met Ryan, I saw a peer as opposed to a professor. But little did I know that he is an expert observer when it comes to supernovae. So supernovae, they're the massive stellar deaths that produce remnants, and he studies these things. He studies their physics, he studies how they relate to the universe at large. What can you say about the fate of the cosmos and about its contents? And so through talking with Ryan, I became inspired to be an observational astronomer myself. He obliged, and he sent me, before graduate school even started, to Las Campanas Observatory in Chile. So get this, I am a new student, and I am told that I will go to Chile to work on the SPQR telescope here for 10 nights. And these are winter nights in the southern hemisphere, so they're 15-hour days, or 15-hour shifts, really. So I'm there with my first introduction to astronomy using this telescope, the SPQR telescope, a 1-meter telescope, for 150 hours. So it was pretty grueling, but right away it let me know, do I actually want to be an observer? And the answer was yes. And furthermore, it gave me this really rich physical understanding of what it meant to observe and how to conceptualize that process, which comes into play later on in the story. So I get back to Santa Cruz, and Ryan floats this idea. Why don't we hunt for the optical light counterparts to gravitational wave sources? That's a big statement, and what I want to do is unpack that a little bit. So I'm going to take you to the state-of-the-art in astronomy thousands of years ago. And that's looking at the night sky and observing. So this was the state-of-the-art for thousands of years, to look, to make careful observations, and it didn't really get more sophisticated until the 17th century, when Galileo turned his telescope to the heavens. When he did that, he saw the moons of Jupiter. He saw the texture of the moon as actually being mountains and craters, and there's topography. So it was surprising. Ever since then, we've been building bigger telescopes that can see deeper into space, which means we can see further back into time. And we even see colors now, colors that we can't see with our eyes, X-rays, radio waves. And that's pretty much how astronomy was, until about the beginning of the 20th century, when there was a glimmer that it could be different. And that came with Einstein. Einstein is most famous, probably, for his equivalence of mass and energy, but he's also equally famous for his conception of what gravity is. He posited that gravity is actually a curvature of space and time. So you can see this animation, this test mass moving around, changing the grid. So he thought of gravity as a curvature of space and time, and part and parcel to that theory are that gravitational waves should exist. So what are gravitational waves? Well, gravitational waves are the literal stretch and strain of space and time itself. And we ought to be sensitive to these things if we only had a good enough detector. And in fact, it was almost 100 years after their prediction that we did detect them with the LIGO detector. Now, this is incredible that we not only confirmed Einstein's theory, but also with incredible precision, we're able to measure distances to 1,000th of a proton to be able to get this detection. And for that, LIGO scientists received the Nobel Prize. But black holes aren't just a clever name. They're black for a reason. They're so massive, they're so dense that light can escape. So as an observational astronomer, I want something else. And neutron stars can offer that. So I mentioned earlier that Ryan was an expert with supernovae. And supernovae, they leave behind a remnant, and in this case, neutron stars. A neutron star, then, is the core of a massive star, and it's composed mostly of neutrons. And so we're talking about something the size of a city that weighs as much as the sun. And as these two objects are orbiting each other, they're bleeding away their orbital energy in the form of gravitational waves. And so as they get closer and closer and closer, they start to rip each other apart and spill their radioactive guts into space. And that produces this sort of emission that we call a kilonova, and that's what we expected to see if we ever did detect merging neutron stars. So there's a catch. If you guys will do me this solid, close your eyes, hold your hand in front of your face, and snap. Now put that above your head and snap. You can tell it's a little bit difficult to see where that sound is coming from. In the same way, LIGO detects like an ear. And so when LIGO detects these gravitational waves, you see these big air regions superimposed in the sky, and they can be hundreds of square degrees. For instance, this September 14th, 2015 region is about 230 square degrees in the sky. So basically, LIGO is saying, we detected something, we think it's over here. Right? So how do we find that as astronomers? To put this in perspective, the full moon is 1/4 of a square degree. So if I shrink this full moon on the scale of those regions on the map, well, you're not going to see it, because there would be almost 1,000 full moons that could fit into that September 14th, 2015. And the story gets a little bit richer. There's a David and Goliath aspect to this, because some of the major collaborations that are looking for these signals are actually spanning a dozen institutions, and they have huge telescopes, and they have hundreds of scientists. And to kind of put that into a visual, here's the Blanco 4-meter telescope compared to the Swope telescope, that red square. So we're talking about the Blanco telescope having 16 times the light collecting power and 12 times the field of view. So they're roughly getting 200 times more photons or packets of light than Swope is. So how can we compete with that? Well, like David versus Goliath, we compete with that with agility and cleverness. So in particular, our collaboration is called the 1-meter 2 hemispheres collaboration, and it consists of a telescope at Lick Observatory in California, and that's associated with the University of California, and the Swope telescope in the south that I already mentioned. In addition, instead of brute force imaging that entire region that we saw, which would pretty much be a fool's errand with a, looking through a straw telescope, instead we're going to target where most of the mass is. We're going to target the galaxies, and it turns out that the universe is clumpy. So we can make intelligent decisions about where to look as opposed to just mowing the lawn, as it were. So it took me about a year to put together this idea in the form of software tools and an actual protocol that we could follow if LIGO sent us an alert. This is an image of the Niels Bohr Institute in Copenhagen, Denmark. So about a year after my time in Chile, this last August, Ryan and I found ourselves at the Niels Bohr Institute at, serendipitously, this basically workshop for gravitational waves. Now, I was there in a different capacity, doing my own research, and we worked like dogs for a few days, and then we took a holiday. So Ryan decides to go to Tivoli Gardens with his girlfriend, and I decide to go to the Louisiana Museum of Modern Art. So, ticket in hand, walking out of the door, the universe had different plans. So, as I was walking out of the door, I received an email from LIGO saying that there was a new detection. And not just a new detection, 2 neutron stars. Okay, this is the Holy Grail detection. And it had a false alarm rate. So the way that LIGO quantifies how much they believe their detection is by describing it in terms of a false alarm rate. This false alarm rate was 1 in every 10,000 years. So 1 in all of the civilizations of Egypt combined, did they think that they were wrong? In addition, we can see here on the top data from the Fermi telescope, which is a space-based gamma ray detector, and LIGO on the bottom. So prepare yourselves. You're about to hear a gravitational wave and a gamma ray burst. On the bottom, you can see this crescendo in cyan, which is the LIGO detection. And believe it or not, that's actually what a gamma ray burst sounds like. So this is so extraordinary because I had just gone to a lecture where Ryan told me that it was unlikely in the next decade that we were going to see a gamma ray detection associated with a gravitational wave detection. In fact, we might not even see it in our lifetime. So this is absolutely bananas. And speaking of bananas, here's the yellow banana that corresponds to the LIGO uncertainty region. Now, I made this analogy between our hearing and how LIGO detects things. Well, it turns out that there was also another detector called Virgo in Italy that had a hand in this detection. So imagine having 3 ears. You'd be able to triangulate things much better. So because of this, we went from hundreds of square degrees in uncertainty to about 30 square degrees in uncertainty, which is definitely a tractable problem with the 1-meter telescope. Okay, so all of a sudden, the race is on. About 60% of the world's astronomers are all looking for this thing at the same time. And where am I? I'm in Copenhagen without phone service, and my boss is on a date. So I text him. Stop what you're doing, please. There's a neutron star detection. I give him the spiel about 1 in every 10,000 years. There's coincident neutrinos, gamma ray burst. And he says, this sounds like a joke. So we go back and forth, and I'm trying to implore him, convince him, with reasoned arguments that this is actually a real detection. And in the process, I'm making hamburger of my coordinate transformations, and he thinks that I'm just messing around. So it gets colorful, so I apologize for that, but you have to understand the moment. And it ends with a supplication that finally does change his mind. So Ryan comes to the office. And by this time, you know, the sun has set and moved on from Africa, and now the night is creeping across the Pacific Ocean, and we're waiting for night to fall in Chile. So we've got 10 hours before we can even start looking. But what I want to draw your attention to here is a sky map from the perspective of the SWOPE telescope. The shaded region you see is actually below the horizon, so there's no hope for SWOPE to see that. And the red little gash on the side, that's the LIGO uncertainty region that we want to search. And if you look at this red arrow, and it's moving from your perspective to the right, the whole map is going to translate that way over time. And really, we only have an hour to look for this thing before it dips below the horizon. So, okay, we waited 10 hours. We furiously were putting together observation lists. I was taking all this knowledge that I had gained over the year of building this pipeline, and we had an hour to find it. And you can imagine there was an intensity, there was a fervor to trying to get everything together. So the situation is we have astronomers at Santa Cruz that are actually receiving the data from the telescope, reducing that data and comparing it with archival information to see, hey, is there something different? And then we also have me and another graduate student and Ryan in Copenhagen actually at the NERV Center typing things to people in Santa Cruz, but also communicating with the observers in Chile to make sure that they observe things in the right way. And so I just want to prepare you for a lot of motion right now as our chat log goes forward. So this is us chatting, bundling targets together, downloading data, and this is Charlie, who is in Santa Cruz saying, okay, nothing in this field, nothing in field 12. And then here you go. This is the moment, I think, when the hairs in the back of my neck stood up. Found something. And you can see that I'm speechless. It's just an exclamation point. I've lost the words, and in some ways, I still don't know how to accurately describe the feeling. And I think the best visual I have for communicating to you what the feeling is like is an image of my daughter that I just had a couple months ago. So this is her. And she still makes this face when I recall this story and I tell her how I messed up my coordinate transforms. So here we are. Charlie sends us this data here, and this is the before image. This is the image before our image. And then he sends us this. And that might have been hard to see, but there actually was a point of light there that showed up in that image. So I'll make it bigger for you guys. So here, this is the discovery image of a new kind of astrophysical transient. And it's easy to see which one of those points is the actual object because, well, one second. Because there's a red arrow. Okay, but in all seriousness, this archival image, we happen to be lucky enough for the Hubble Space Telescope to have imaged this field some months prior. And you can see on the left, there isn't a dot where the arrow is. On the right, there is. So it's just as simple as that. When you write a discovery paper, you basically said, we looked, and it was here. So I want to go back and I want to emphasize the team that made this discovery. Okay, so you're going to hear from Enrico right after me. But there's Ryan, and you guys have seen his picture. Everyone else in that slide is a first or second year graduate student or a postdoc. I think that's remarkable. We had a 1-meter telescope. We didn't have a 4-meter telescope, right? I came into this program without a huge amount of, sort of experience, but I was able to make a significant impact coming into a department like Santa Cruz's. And I think the image that really typifies that is the fact that we got the breakthrough of the year. So to give some more details on that, I'm going to have Enrico come up to the stage and talk about what this means.
So I'm going to tell you why there's an August 17th event in all of us. I'm going to take you through the history of gold production and element production in the universe, and hopefully I will convince you that we ourselves are the fossil record of chemical evolution in the universe. And of course, I'm going to use Carl Sagan's words, which says, the beauty of a living thing is not the atoms that go into it, but the way that those atoms are put together. So we are atomically unbelievably numerous. There's more atoms in our body than actually stars in the entire universe. We have 10 to the 27 atoms in our body. Yeah? And those atoms have a vast memory. Yeah? You can talk to your hydrogen atoms about the Big Bang when they were first produced. Yeah? You can talk about the helium atoms also about the Big Bang and the first 3 minutes in the history of the universe. And you can talk about all the generations of stars that have ever been formed, exploded, and recycle those atoms, yeah, all the way until today that are now sitting in our bodies. So we are slightly different than the universe in the sense that the majority of our mass is actually made of oxygen. We're 65% oxygen, 18% carbon, about 10% hydrogen, which of course, as you know, is the most abundant element in the universe, which was made in the Big Bang. And we also have a significant amount of nitrogen. And each of these elements has a story on its own. And of course, because I don't have as much time, I'll tell you about, of course, the most important element, because we are, as humans, self-centered, which is oxygen first. So, the oxygen that we breathe, the oxygen that made the majority of our body, was in fact catalyzed in a massive star. in a star that it's about 10 times the mass of our sun. It has about 1,000 times its luminosity. These stars are sort of the Elvis Presley of the universe. They're extremely luminous, but they live very short lives, because they exhaust their fuel so rapidly. One of these stars has about 10 to the 58 atoms, and they fight their struggles against gravity. Gravity wants to compactify the star, and the star is actually going into nuclear reactions into the interior, generating heat and preventing gravity from winning that battle. And that fusion of elements goes all the way to iron. And iron, as you know, is the most stable nuclei in the universe. And that means that the battle is basically lost. Gravity has won. No more fusion can actually take place that gives energy to the system, and the star collapses. And it is in that collapse that a neutron star is actually formed. So I'm going to show you a simulation here of the core of this massive star. And again, in the core, everything is happening very quickly. You can see in a fraction of a second, the majority of oxygen in your body is going to actually be produced. What you're seeing here is entropy, or temperature. So the temperature is increasing. Energy is being accumulated in the core of the massive star. The entire core is basically collapsing, so there's material constantly falling in, heating up this interior until enough energy actually is confined that you go from an implosion to an explosion. And so much energy is actually generated that it basically tears the entire object apart and leaves this neutron star in the core. And it's in that edge that you see where actually the majority of oxygen is explosively made. One of these supernova explosions, like the ones that David and Ryan studies, when it explodes, is actually as bright as the entire stars in a galaxy put together. And that's how we can find them. Yeah. We can go closer to home and look at these beautiful supernova remnants. And I want you to visualize that the majority of the mass in your body came from one of these supernova remnants. Yeah? The oxygen here was basically ejected into the gas, mixed, and then gave rise to new generations of stars. Yeah? So we are a constant recycling of these steady, beautiful luminosity to this violence to rebirth again into new generations of stars. In our bodies, we have about hundreds of thousands of supernova, at least the memory of it. Yeah? Now, oxygen in particular is one of my favorite elements because it's constantly recycling the atmosphere. The atmosphere actually doesn't lose a lot of oxygen, so then you can think about, well, not only the universe is recycling oxygen, but we are recycling oxygen. I go about 550 liters of oxygen a day, all of us do. I'm lucky enough to be standing in front of you and stealing some of your oxygen atoms that you came in with, and I'm going to take them away. Yeah, and I'm hopefully sharing you my good oxygen atoms. So what does that mean? That means that we're not only the fossil record of the universe, we're also the fossil record of humanity. Yeah? So you can do a calculation and say, well, how many atoms I have of Shakespeare? Well, about 1 million atoms of oxygen in my body once belonged to Shakespeare. About another billion of atoms in my body belong to Frida Kahlo or to Cesar Chavez. And of course, you can think about the atoms that you don't want to know. Yeah? But you can choose and pick your atoms. So that means that all this unleashed creativity of humanity is actually in our bodies. And the reason is because we are atomically so numerous. And then we go to sort of the central theme of our talk, which is gold. Yeah? In that beautiful shining light that Dave and Charlie saw for the first time, we also saw the production of heavy elements, and in particular gold. What it's giving power to that source was actually the radioactive decay of heavy metals. and in particular gold. Yeah? So Dave is sort of an alchemist in the sense that he's not making gold, but he's deciphering the origins of gold. And as I hopefully will guide you, actually coming up with a recipe of gold really is beyond humanity, because these systems require the largest densities in the universe and the largest temperatures ever to be manufactured. And then you say, well, you convinced me that I should care about oxygen and I should care about supernova explosions, but you should also care about gold, because we have about 10 to the 18 atoms of gold in our body. And if you like sushi, you probably have higher concentrations of gold in your body. So gold is not highly abundant. Here in this table, I show parts per billion. So the universe is about 0.6 part per billion by mass of gold. The sun is about 1 part per billion in weight. Meteorites are actually highly enhanced in gold. They're about 170 parts per billion. And one of the reasons why we actually want to go and mine asteroids is because they're highly enhanced of these precious elements. Crustal rocks also have significant enhancement. But if you ask yourself, where is most of the gold today that it's actually available for extraction, it's actually in seawater. But seawater has very small proportions of gold, about 0.05. And thankfully, humanity hasn't found a way to actually economically feasible extracting that gold. But we humans are extremely metal-rich. Compared to the universe, we're 50 times more abundant in our gold content than the universe. Yeah? So we are precious. If you actually think about sort of the quantities, all the gold that has ever been mined is about 160,000 tons, which is about the size of 10 buses. Yeah? And the majority of that gold is in a vault, and only about, a few percent is actually done for jewelry. So I have to go back to my origins and give credit where credit's due. The Aztecs actually thought that the origin of gold was the sweat of the sun. They thought the sun was sweating these pieces of gold that we can find highly concentrated. And you can say, well, Enrico, but you told me the gold is 1 part per billion. Then I could be walking around, especially at the time of Shakespeare, and find these gold nuggets. Yeah? And that's because in these crustal flows, gold gets highly concentrated at high pressures. And that's why it's easy to find. Well, the Aztecs were not completely wrong, because there are a significant amount of gold in the sun. As I said, 1 part per billion. So how much gold there is? Well, if you extract the entire gold of the sun, you get about the mass of Ceres, which is the largest asteroid in the solar system. This is to give you a perspective. It's about 900 kilometers or so. Oops. Too sensitive. So this is the price of the sun in gold. Yeah? And this is about $10 per gram. So this is the price of the sun in gold. And I'll tell you a little bit about the price of Dave's discovery. So for 15 years or so, I have been working on this idea of how gold is made, this recipe of gold. And the ingredients are, we need the densest object in the universe. It has to actually have a companion, which also happens to be the densest object in the universe. You have to merge them together at billions of degrees Kelvin, and then gold will come out. So neutron stars, as David mentioned, they are the size of the San Francisco Bay, but the mass of the sun. So they're the densest objects of the universe. If I was sitting in the surface of a neutron star and I wanted to escape, I have to move at 30% of the speed of light to be able to escape the gravitational force from that object. Yeah, they're the densest objects in the universe. They're rare. A bucket of neutron star material weighs as much as Mount Everest. The density of neutron star material is about 10 to the 14 in units, where the density of water is 1. So they're 14 orders of magnitude denser than water. About 2% of all neutron stars are members of a binary system. That means that they're orbiting around a companion, and they have basically a company throughout their burning heavier elements. About 1% of those neutron stars have another neutron star. So it's the 1% of the 1%. So 1 part in 10,000 of all neutron stars in the Milky Way, which are about 100 million of them, happen to have a companion. So they're very, very rare objects, and that was one of the reasons why this theory was actually put into question for a long time. These objects spend about 1 billion years orbiting around each other, losing energy and angular momentum through the emission of these gravitational waves as they distort space and time, slowly coming together. Until they basically become what we call dynamically unstable. They sort of collide with each other. They increase their temperature to billions of degrees Kelvin, and this is where we think gold production actually took place. I'm going to show you here one of the sensitivity of this device is letting us down. I'm showing you here the last in spirals of 2 neutron stars. This is a computer simulation that took about 2 months in 1,000 processors. What you're seeing there is temperature or entropy. So these objects touch each other, eject material in what we call these outer Lagrangian points, these beautiful spiral tails. And it's in those spiral tails as they move away where gold is actually produced. And that was the theory. Yeah? So it was an extremely rare event that produced a lot of gold. And that was one of the reasons why it was put into question. In fact, if you open any textbook, it says that the majority of heavy elements in the universe above iron come from supernova explosions. The same supernova explosions that give rise to your oxygen. So for the past decade or so, I've been working on this subject and getting some interesting emails from my colleagues about how it's completely crazy that the majority of the gold in the universe actually assemble in these very exotic events. This is about January 2011 with a world-renowned astrophysicist, which we'll rename nameless, that says the idea that mergers are able to enrich the universe with heavy elements must be rejected as a physically impossibility. Yeah? And it took us about 5 years to convince that our argument was indeed incorrect. And at about April of 2017, The Atlantic published an article which says the mysterious origin of our galaxy gold. And it says, after long believed that exploding stars, supernova, forge these metals, researchers now are divided over which extraordinary cosmic event is truly responsible. So that means that after a decade or so, we were just starting to accumulate clues that, in fact, we may be right. And there's a beautiful quote by a good friend of mine that says, if LIGO, this amazing instrument, still has not found something, there'll be a moment in which myself and my colleague Brian, which were quoted in the article, should wander and get back to the Bohr. That means you should do something else. You have devoted a decade of your life, you may be wrong, and you have to start facing the consequences of that. And of course, August 17, everything changed. And I was lucky enough to be part of this wonderful team. I'm a fake astronomer. That means I don't look up at the sky, I look at my computer screen, but I get to work with these amazing colleagues of mine. And the glow that you're seeing of this source is really powered by the radioactive decay of precious elements, things like gold, platinum, silver. Yeah? So this is sort of the dream of astronomy. For about 30 years, half of the elements heavier than iron, we didn't really know their origin. And now, thanks to this wonderful group at UC Santa Cruz, we now know the origins and we can pinpoint it. It is breathtaking to me to think about the creativity and strength of our group. Dave mentioned that we were sort of the underdogs, but I felt we basically use strategies in place that will get us ahead of the game. And one of those strategies at UC Santa Cruz is actually invested in our youth. If you look at the students that are represented here, we have Cesar, who's from Costa Rica. We have David, of course, who is not a non-traditional student in the sense that we were able to lure him back to science. We have Ariadna, who's from Mexico. Matt, who is an incredibly talented undergrad student. We have Enya, who's from Serbia, or formal Serbia, and then we have Charlie. And a testament, really, of my colleague Ryan Foley is that we published 6 papers, 6 really breakthrough papers, and every single one of those is actually led by a grad student or a postdoc. They had, as you can see, the entire glory of this discovery, and they deserve it because they did all the work. So in Santa Cruz, we do invest in students. So how much gold is created in one of these events? So this is actually what we set up to do. And here you see, this is a Nature paper with my colleague Brian, which was named in that article. Well, one of these events produced about a Jupiter mass of pure gold. I mean, remember, you immediately say, well, but in the sun, there's about a Ceres mass of gold. What's going on? Well, one of these events produced a huge amount of gold. And in fact, it's enough to supply of precious elements to about 6 million stars. Yeah? So this was actually one of the arguments why people were very skeptical that these rare phenomena could produce as much gold in order to supply the entirety of the galaxy today with these precious elements. And of course, these led to the breakthrough of the year, and I have to really talk about Dave, even though he doesn't like to be talked about. Dave basically wrote the most important article in the Science journal, which now has about 110 citations. His paper has been cited more than once every day since it was published. There's always a scientist in the world that is getting to know Dave. And it's really a testament to his perseverance and his creativity. Yeah? I mean, he made it happen. And I'm really, really grateful that you proved me right. Now I can retire, so thank you, Dave. So I wanted to just take you to a final journey as to where ultimately that gold and how that gold ultimately comes to us in this sort of journey of recycling of metals. So as you know, all of these explosive phenomena throw out metals all the way into the universe. They get mixed with gas and new stars are formed. What you see here is the formation of our solar system, where the sun was actually formed from this rotating cloud, which created this sort of pizza structure where basically our planets are made. But something that is extremely interesting is that when the Earth was actually made, it was molten, which means that all the heavy elements sank into the center. And for a long time, people actually debated, well, where is the gold that we find in the surface? Where does it come from if all the gold on Earth is actually at the core? And the answer is, it came from the late bombardment. It came from basically asteroids that impact the surface of the Earth. As you know, asteroids are about 200 times more abundant in heavy elements, and therefore they sort of painted the surface of the Earth. Those metals mixed in the mantle, concentrated, and then came back, and that's where we basically built mines. So in the spirit of Santa Cruz, I thought it was fitting to end my talk giving you a myth. Yeah? This is a myth from the Olmecas. If you don't know the Olmecas, they're this Mexican culture that have these beautiful sculpted faces. There are these huge sculpted faces in Veracruz. They have very, very small noses. A lot of people say that I look very Olmeca and make fun of my nose in Mexico. That says the following: at the moment you are conceived, your essence, as it tries to reach you, breaks into 1,000,000 pieces. So the same way that the gold is ultimately delivered to Earth by asteroids, your essence is delivered to you, but it's basically broken into 1,000,000 pieces. And my grandfather used to say, well, but, I mean, one of the consequences of that is that when you start, gaining consciousness and realizing who you are, you're going to feel slightly incomplete, slightly empty. But that's actually an opportunity, because those pieces, rather than basically be scattered around and you having to pick them up from the streets, fell into other people. And it's only by sharing those pieces with other people that you become more complete. Yeah? And the natural consequence of that is that every single piece is important in your journey to become complete. And there's going to be people that are going to give you these very, very large pieces and are going to make you very happy, and there's people that are going to give you smaller pieces, yet they're going to be necessary for you to be complete. And to me, that really captures the essence of what UC Santa Cruz is, and the belief that we have in our students, and the way that we contribute all together in science. So hopefully the next time you look at your gold ring, you will remember that in order to produce that ring, it took the two densest, most exotic objects in the universe that happened to live together, that happened to meet almost their entire rest mass energy in gravitational waves to come together, to be merged in billions of degrees to ultimately make gold. And I'll stop there. Thank you.
So let's invite all of our speakers onto the stage, and we'll take some questions from the audience. I don't know about you, but my brain's working overtime on a Monday night. Whew, that was a lot of stuff. So, why don't you guys go center stage?
Center stage.
We'll take any questions about any subject, whether they spoke about it or not. Anybody? Yeah, it's right here in the red.
What did NASA say about it? If they heard it, or if you got a response?
So is that question directed at me?
To whoever wants to.
Okay.
You should answer it. Yeah.
Yeah, well, I actually, I had an advisor at NASA Goddard Space Flight Center. Before I did sort of transient astrophysics, I did some work with galaxies. And so my advisor, Ryan, he goes to the National Science Foundation. There's a big press release to sort of publicly announce this, because all of this transient stuff and LIGO stuff, it's all kept under wraps until all the people have sort of positioned themselves to write the papers they're going to write, and they sort of let the world know so they can't get scooped. And I get a text message as Ryan is mentioning me in his conversation from Ann Hornschmeyer, who, she's like pretty high up at NASA, saying, "Is that you? Is that?" Yes, it's me. So I don't know what NASA said generally, but I know what she said. So I think, in all seriousness, NASA, chemical evolution, galaxy evolution is a big deal at NASA, and I think that they've been looking for stuff like this as well. So the partnership with LIGO and with observatories using Hubble Space Telescope and other resources that NASA helps to maintain, I think that everyone was looking for this. So.
And you can say that the vast majority of satellites from NASA saw these events.
Yeah,
follow this event.
I mean, I think you mentioned it before, that this is the most observed phenomenon ever, in terms of how many telescopes in Earth and in space were trained at it.
Wow. Down here.
I am a neuropsychologist, and I'm so worried that this question is going to sound stupid, but I've been wondering the whole time, how did your discovery prove your theory about voice?
I didn't make my point very effectively. So of course, as we teach our students, there's not such thing as stupid questions, only profound ones. So, we have speculated that when two neutron stars come together and merge, they will basically eject these precious metals. And the telltale sort of signature of that is, as those metals expand, moving at a fraction of the speed of light, they're radioactive, so they're basically decaying, and they're heating this material. So this material glows. And the glow that David saw matches the prediction of how a ball made of precious elements needs to glow as a function of time in order to be responsible for producing those metals. And in fact, that's how we calculate the total amount of mass, by calculating the total amount of energy that this ball, expanding ball actually goes. So we were able to measure its velocity. We knew that this thing was moving at 0.2 of the speed of light, 20% of the speed of light. We were able to measure its luminosity, its distance, and therefore, we put together a pretty consistent picture. And in fact, the predictions which were made before the event actually fit the event relatively well. You too.
Sorry.
Right here.
There was a number that you associate with the dollar amount of the gold. I want to know, can you name that figure?
I'm sure it has a scientific number, which I don't remember. So just to give you a feeling, like, let's try to put a number to Dave's discovery. So, about 1 gram of gold is about $10. A Jupiter mass of gold is about 10 to the 30 grams. A 1 followed by 30 zeros. So basically, a 1 followed by 31 zeros is the amount of dollars that Dave's discovery is worth in terms of gold. But yeah, those numbers are even difficult to imagine.
Right. But you can think of that exponent, right, 10 to the 31, as being the multiplication of 10 to the 12, which is a trillion, times 10 to the 12, which is another trillion. So that's 10 to the 24, plus another 10 to the 7 to get 31.
Which is 10 million.
Right.
And then you're
right.
Like, wow.
So imagine 10 million envelopes, and each side, one of those envelopes is a trillion envelopes. And inside each one of those trillion envelopes is a trillion envelopes. And just put $1 for each one of those envelopes.
The check is in the mail.
The check is in the mail, right?
Somebody over here.
Hi, I just wanted to say congratulations to you, Dave and Enrico, both on this amazing discovery. But I was just wondering, so right now gravitational waves and LIGO is a big deal for astrophysics, and it's still going up. So what is the future for you, Dave, and what is the future for you, Enrico? What is the future of your research?
So I'll start with that. So you're absolutely right. The next generation of LIGO is coming online around November of this year. And so the cat's out of the bag. People know that these kinds of phenomenon exist. And what's more, as LIGO gets more sensitive, we think that our detection frequency is going to increase as well. So these events, maybe they're not neutron star mergers, but they're black hole mergers maybe, could be as frequent as a few a month. And so I think it's going to be an embarrassment of riches on the one hand, right? We're going to have lots of different detections, and we're going to have to make intelligent decisions about which ones to devote all this telescope time in order to get not just the evidence that these things are possible, but understanding what they are as a demographic. What do they say in general about chemical evolution or about the end stages of stellar evolution? So for me specifically, though, I'm sort of the Hephaestus of our group. I build the tools, I make the databases, I create the logic. And so there's going to be an infrastructure piece for me where I basically take everything I did and just put it on steroids and make it something that can respond automatically to an alert from LIGO. I can imagine getting a text from my phone next time that says, oh, there's an alert, but instead of me having to work for 10 hours to figure out what I'm going to do, the computer will give me suggestions of what I should do, right? So I think from an observational point of view, it's really going to be about maximizing the resources that we have and making sure that we have these proposals written to get the telescope time to do the follow-up. Because that's where the really interesting part's going to be. It's going to shift from discovery to follow-up. I think, just one last point is that we did this with a 1-meter telescope, and there are 1-meter telescopes all over the world. So in the future, it's going to be where you're at. If it happens to be night, and it happens to be above you when the alert goes out, you're probably going to find it with this kind of technique of aiming at the mass in the sky, aiming at the galaxies. So that's what I think.
Over here.
Did those two stars orbit each other?
We think so. Yeah, we think so. That's the model, that they had been orbiting each other for something like at least 1 billion years.
So we see in our own Milky Way, so these collisions happen, how far away, Dave?
It happened about 150 million light years away. And so because the speed of light is constant, looking 150 million light years away is like looking 150 million years ago. So think the late Cretaceous, flowering plants were just starting to be evolved on the planet Earth. That's when these things collided.
But in our own Milky Way, we know of about 20 of the systems that are already orbiting around each other where there's 2 neutron stars. And in fact, the Nobel Prize in the 90s was given by actually finding that these 2 neutron stars were actually coming slowly together, sort of making, true the prediction of Einstein that these systems actually emitted gravitational waves. So yeah, these systems are orbiting around each other.
Down here.
Getting back to Caesar.
Yay.
You called?
If you were to cast Caesar using current political theories, aside from the obvious Orange Julius, who would you cast into each role?
I'll just take the title character, and it would be Theresa May. One of the things that is so conspicuous about Shakespeare's Caesar is his manifest imperfections and incompetence at politics. I hope there are no British subjects in the room. Caesar is described in the play as being deaf in one ear and having epileptic seizures, and he's extraordinarily vain. And he's the least probable character in the play to have attained the position that he holds. I guess that's drawing him a little closer to home. But at the moment, I think that figure is actually Theresa May. She's the Prime Minister of England. She's uniquely unsuited for the challenges of the divisions in her society. She's presiding over the separation of England, or the United Kingdom, from Europe, which she voted against. Right. So, I did an assignment in the Shakespeare course I taught this quarter, where the students were invited to. They could do a traditional assignment, or they could do a creative assignment. The creative assignment asked them to reinvent the play, to redesign the play for a setting that was anywhere on the face of the earth and at any time in our history but ancient Rome. And that produced some really remarkable casting. So maybe the students' responses are the best ones. They set them in hip-hop recording studios and imagined that Caesar was a record executive in a conflict with a star. Right, a rising star who was about to change allegiances. They set them in online environments in a kind of ongoing popularity war between people who only exist as avatars to one another, and explored the possibility of character assassination using the internet. Right. So that assignment really showed me that very few, actually, of the responses to that assignment were political in nature. One student who's just arrived from China set the play at this moment as the Chinese president is about to have himself declared president for life. So he set it in contemporary Beijing. But overwhelmingly, the students understood about the play in our moment now that the political questions that it raises are much less interesting than the communications questions that it raises, right? Do you want to wall yourself off from other people in a society in which language has become poisonous and weaponized? Or do you want to extend yourself to other people by listening to them and talking to them at the risk that you will become an instrument of their own will and agenda? So I think the students understand that what we should be talking about in Julius Caesar is the degree to which we should be persuadable by each other.
So I want to wrap us up and thank everyone for coming. And please continue the conversation down the hall for dessert and coffee. Thank you for coming.
Very good talk.
Can we go to Austin? Can you take these off?
Yeah.